All right, so we're going to do an introduction to line integrals. So, start with a surface. Consider this surface z equals f of xy. And what we're going to do is look at this dotted curve C. Okay, so you see that curve in the xy plane C. This curve in space that lies on the surface F. Okay, let me highlight that a little better for you. This curve right here, and it lies on the surface right there with the xy values that lie on C. So remember, C is this curve in the xy plane, right? So it's like the area above that curve C, but below where it intersects with that surface F. This area can be found with a line integral. So what the line integral does is it finds this area of that sheet right there, okay? The area under the curve of that surface on the trajectory of that C curve in the xy plane. It's like you take that z function and project it down to the xy plane. It makes that C line. Now, C is a smooth curve that is parameterized by S. So we parameterize that curve by S. Just like we did parameterizing earlier in the course, we parameterize with the arc length parameter. Now, calculating the arc length parameter can be tricky, but another way to write this is the integral over the curve C of f of s, where s is that arc length parameter, and we integrate with respect to the arc length parameter. So what are we doing? We're summing up along the curve C. Sum along the curve C. What do we sum up? Function values f of s times multiplied by my change in s, my change in small arc lengths. That's what we're doing. So if C is a closed curve, meaning it ends at the same place it starts, so in this example, your C looks like it's just a line, so that's not a closed curve. But in a closed curve would be like it starts here, it runs around, and then it comes back, and it stops at the same place. So if C is a curve like this, then what are we going to do? To designate that, we're going to put a circle on my integral symbol, okay? And that represents a closed curve C. Now, if C is a curve and S is the arc length parameter of C, and S is between A and B, inclusive, then the result is the line integral over the smooth curve C, parameterized by the arc length parameter S, is equal to the integral from A to B with respect to S. Okay? This hopefully looks familiar to you. So how is this really even any different than when we were in Cal 1 and we found the definite integral, which was the area under the curve, right, from A to B, f of x dx. Well, the big difference here is instead of having a variable x on that x-axis, we have our variable here, s, which is the arc length parameter, right? So in a way, it's almost like we're kind of doing that same thing, but now we're not just considering it on that x-axis. So the real difference with this integral from the standard integral from a to b f of x dx we used in the past is that of context. Our previous integrals naturally added up values over the interval on the x-axis, whereas now we are summing up values over a curve. Okay, so this curve doesn't have to be a straight line. Like I said, it could be a closed curve like that. If we parameterize the curve with the arc length parameter, and remember that arc length parameter, we have those consistent breakup measurements, right? We can evaluate the line integral just as before. Unfortunately, parameterizing a curve in terms of the arc length parameter is usually pretty stinking hard. So to overcome this, we have to develop a parameterization technique. And that's where we're going with this theorem. Theorem 14.1.1, evaluating a line integral. Let C be a curve parameterized by r of t equal to the vector with component, x component, that first component, g of t, and y component, h of t, for t between and including a and b, where g and h are continuously differentiable, and I'm going to let z be continuous over. So z is that surface on top of or below that xy plane, and it's continuous over that curve C that we are evaluating our line integral. If that is the case, and we can parameterize C with a function, for example, if I had in the xy plane the circle, the unit circle, how would I parameterize that in the xy plane? R of t would look like what? It'd be cosine t, comma sine t. Okay? So if I can parameterize, then that terribly difficult arc length parameter goes away, and in its stead, I can replace the first component, g of t, with that first component there, that second component, h of t, with that component there, whatever that function is, and then evaluated, multiplied by the magnitude of the velocity, okay, the derivative of that parameterization with respect to t. So if you get nothing else, you need this right here. This is your key to help you avoid having to find the arc length parameter, which is really hard to do. Same thing works for a curve C parameterized in space. So I know we talked about parameterizing it just in the xy plane, but all you have to do is add a z component, and if you can parameterize it that way, that's all you got to do. Same rules apply. You just add in that z there. All right, so let's get to an example. I want to use a line integral to find the area under the surface f of xy equals cosine x plus sine y plus 2 over the curve C. So this is a segment of the line y equals 2x. But we're only going from x negative 1 to x equal to 1. So that segment, that C right there, is that curve. All right? It's the line from negative 1 to 1. So, how are we going to do this? How are we going to do this? Think back to what our formula said, okay? Our formula so we have integral, line integral, C, f of s ds equals the integral from a to b of f of g of t, comma, h of t. And so then what we're going to do is going to multiply by the magnitude of r prime of t dt. Okay? So, our job is to figure out what in the world is r of t. Okay? If we can find r of t, then this problem is just going to be plugging and chugging. Okay? So I need to parameterize this curve here, which is a line. Now, the independent variable is x, and the dependent, y, is dependent on what input for x, right? So y is equal to 2x plus 1. So if I'm going to parameterize this, okay, then this g of t part, the independent variable, is t, and at any given value, if I want to get the y value, that h of t, then I need to do 2 times t plus 1 to get the y part. Okay? So if I do that, now I've got this function, r of t, is t, vector value function, t, comma, 2t plus 1. And what is it good for? What values of t? It's good for t between negative 1 and positive 1. That's where it's defined. Okay? So what all do I need? I need to take my function f and plug in g and h, but I need the derivative r prime. So let's take the derivative. So d dt r of t is r prime of t, and the derivative of t is 1, and the derivative of 2t plus 1 is 2. Okay, so if I want the magnitude of r prime, then this is equal to the square root of the first component, which is 1 squared, plus the second component, which is 2 squared, which equals to the square root of 5. So this magnitude of the derivative is equal to the square root of 5. Okay? This integral c f of s ds is going to be the integral from a to b. Now a to b here, looks like a to b here is going to be from negative 1 to 1. So a to b, from negative 1 to 1 of f of t, comma, 2t plus 1, and then the magnitude of the derivative, which is square root of 5 dt. Now what is f of t, comma, 2t plus 1? Well, when I look at f of xy, I get cosine x plus sine y plus 2. So f of t, comma 2t plus 1, everywhere I see an x, I'm going to put a t, and everywhere I see a y, I'm going to put a 2t plus 1. So this becomes the integral from negative 1 to 1 of cosine t, okay, plus the sine of y. Now y is what? 2t plus 1 plus 2. And all of this gets multiplied by the square root of 5 dt. Okay? Now, when I integrate this thing, the integral of cosine is sine. The integral of sine of some stuff is negative cosine of that stuff. But then I have a chain rule, and if I took the derivative of this inside, I would get an extra factor of 2. Okay? But since I'm integrating, instead of getting an extra factor of 2, I need to divide by a factor of 1/2. And you can do that with a u substitution. If this is too much for you, do a u sub here. And then du gets you 2 dt. And then that tells you 1/2 du equals dt. And you can go from there and you see you get the 1/2. Okay? So this technically, pull that 1/2 out front like that. Okay, and then the integral of 2. What is the integral of 2? Well, I think we can figure that one out. That's 2t. All right, all that is multiplied by the square root of 5. And I evaluate from t equals -1 to t equals +1. And if I put that to work, type it in the calculator, evaluate that, I should get around 14.418 units squared. So that line integral, which tells me this area here, okay, is 14.48 or 418. Okay, kind of cool. All right. Let's take another example here. A planar curve C is given x squared plus y squared equals 1. Unit circle. All right, so we kind of talked about this a little bit earlier. I kind of hinted at how to parameterize the unit circle. You guys have done this a couple times now. But the unit circle, along with the surface, this surface, x squared minus y squared plus 3, okay, pictured below in that first part here, this is defined over C. So what we're going to do is we're going to evaluate the line integral. So when I evaluate this line integral, okay, over C, then the result is this helix-looking cylinder top thing, kind of weird looking thing going on here. Okay, pretty interesting shape. So that's what that line integral finds, that area under the curve on that path, that curve C. So can we parameterize the circle? I think so. It's a unit circle, so to parameterize r of t, it's just cosine t, sine t for t between 0 and 2 pi. That's it. Okay? We don't want to keep going past 2 pi because once we start, right, go up pi over 2, around, well, I guess I could follow the curve, huh? Pi over 2, so 0 to pi over 2 to pi to 3 pi over 2, and then back to 2 pi. If I kept going past 2 pi, I would just keep wrapping around further and further. I only want to go around it once. All right? So I guess at this point, you know, if you had a circle that was, say, I don't know, instead of being a unit circle, maybe it was like x squared plus y squared equals 16. Okay, so that's really like 4 squared. So that means the radius is 4. Then how you would parameterize that, it would be 4 cosine t, comma 4 sine t. So that coefficient in front represents that radius of the circle, if that makes sense. Okay? If it was an ellipse, meaning, look, you know, no longer is it perfect circle, but maybe it looks something like this. Let me try that again. Well, can't get it to quite, but you see what I mean. I mean an ellipse here, okay? Then if that, you know, side had a radius 4 and the other one was still a radius 1, then maybe you would just get rid of the 4 on the y component part. And so that would be how you would parameterize that type of ellipse. So kind of giving you ideas, not saying you're going to have an ellipse, but just in case you did. Okay, so let's tackle this, because remember, formula is still the same. I want to evaluate the line integral c of f of s ds, which is equal to the integral from a to b, f of what? We don't have to call it g and h. We could call it x of t, y of t, if that makes you feel more comfortable. And then what? And then this is the magnitude or the norm of the derivative of that parameterization, dt. So really the key here is, and what the trick of these whole problems is, trying to figure out what r of t is. Once I get r of t, take the derivative, r prime of t is equal to what? The derivative of cosine is negative sine. The derivative of sine is cosine. And then to get this magnitude here, I have to square each component, so negative sine t squared plus cosine t squared, and then take the square root. And once I do that, I get the square root of sine squared plus cosine squared, which is that awesome identity that we've used 1,000 times, 1. So this r of t just becomes 1. How easy is that? So this becomes what? All right, integral c f of s ds becomes the integral from, okay, what is my a, what is my b? I have t from 0 to 2 pi. Okay, 0 to 2 pi. Now, f of x of t, y of t, which is what? It's cosine t, comma sine t, and then 1 dt. So remember what the function is. F of xy is x squared minus y squared plus 3. So everywhere I see an x, I'm going to replace it with cosine t. And everywhere I see a y, I'm going to replace it with sine t. So this becomes integral from 0 to 2 pi of cosine t squared minus sine t squared plus 3 dt. Now, cosine squared minus sine squared is actually an identity. This is the cosine of 2t. Okay, so that helps us out. If you didn't know that, you just have to use, reduction identity, but whatever. Integral 0 to 2 pi cosine 2t plus 3 dt. And now we need to integrate. And when we integrate this, so simple u sub, we don't have to u sub, but if you had to u sub, u equals 2t, du equals 2 dt, so dt is 1/2 du. So I'm just going to do it. So the integral of cosine of stuff is the sine of that stuff. But instead of multiplying by 2, when I take that chain rule, I divide by 2 because it's an integral. Okay? And then the integral of 3 is 3t. Now evaluate from 0 to 2 pi. Fundamental theorem of calculus gets me 1/2 sine 4 pi plus 3 times 2 pi 6 pi minus 1/2 sine of 2 times 0, which is 0. Sine of 0 is 0, so that goes to 0. And then plus 3 times 0, which is still 0. So that whole thing just goes to 0. Second part goes to 0. So what is the sine of 4 pi? 4 pi is, I go around the circle once for 2 pi, and then again. So the y value here is 0. Okay, so that's 0 plus 6 pi. So my answer is 6 pi, which is kind of interesting. 6 pi, that seems like a pretty simple answer for this area here. But look, think about what this function is. It goes down, and then it goes up, and then it goes back down, and then it comes back up. So it's very symmetric in the way it does it. It goes up in the x direction, and then down in the y direction, and then it kind of levels out at 3. So what happens is, since it's centered at the origin, the circle is, these x squareds and these y squareds kind of balance themselves. One takes away and one adds to at different times. So sometimes we're going down, sometimes we're going up in the y value. And so they kind of cancel each other out. So they average out to basically, it would almost be like this whole thing had an average height of what? 3. That 3 there. Okay? So how do you find this here? That area of this shape here, if you think about it, it's just like the side of a cylinder. So the side of a Coke can. So what is that? Well, that would be, if I could find the perimeter of that circle, which is unit circle, has a radius 1. So that would just be circumference is 2 pi r, right? Well, the radius is 1, so that means so the circumference is 2 pi. So if that whole circumference is 2 pi and the height is 3, 3 times 2 pi gets you the 6 pi. So does that make sense? It's just kind of like that. It's averaging out. That's where that 6 pi is coming from. So kind of an interesting problem. Okay. So another example, find the area under f of xy, where f of xy is 1 minus cosine x sine y. And over the curve, so now we're not doing a circle, we're not doing a line, but we're doing a parabola in the xy plane, okay? So my c, this curve c, is in the xy plane, y equal x squared. But it's not the whole parabola, okay? It's only from -1 to +1. So we're stopping. We're only getting this portion of the curve. Okay. So if that makes sense there, that's really what's going on. This is my curve C that I'm looking at in the XY plane. Right? And now my function, my Z surface, is 1 minus cosine X sine Y. And I want to find the area under that surface. So what is that? So like if that's my 3D surface, then this would kind of be that area that it's talking about, okay? Try to do a better job. It's kind of hard to draw all this stuff, but kind of get the idea. Okay. Kind of like how we had here, we had our 3D surface and then we came down and we made that cylinder looking shape. Same thing here. We had our 3D surface and we came down and we had our sheet, that area under there. That's what we're looking for area under the surface, but over that curve C. Okay? So we need to figure out R of t. Okay? R of t, so this vector valued function. Now once again, to me, it looks like x is the independent variable and y is dependent on x. So t for the x component, and how do I get y? Well, if I square t, I get y, because y equals x squared. Okay? So x is equal to t, which implies y equal x squared becomes y equals t squared. Okay, not too bad to parameterize, but this is only good for what values of t? For t between -1 and +1. So r prime of t is equal to the derivative of t, which is 1, and then the second component, derivative of t squared, which is 2t. And when I take the magnitude of the derivative, I get the square root of 1 squared plus 2t squared. So the magnitude is 1 plus 4t squared, which is a little bit different than what we have done in the past. So integral c f of s ds equals the integral from a to b f of x of t y of t times the magnitude r prime of t dt. So this becomes what? The integral from, okay, a to b here, t is stuck between these two values, -1 and +1, right? Now f, the f function, f of xy is equal to 1 minus cosine x sine y. So everywhere I see an x, I'm going to put a t. And everywhere I see a y, I'm going to put a t squared. So this is 1 minus cosine t sine t squared times the square root of 1 plus 4t squared dt. Now, If you can integrate that by hand, you're awesome. Okay, that's pretty hard to do. What I would suggest is that we go at this point, once we have it set up, now we resort to technology to help us find this answer. So go to math and then definite integral, -1 to 1. And then I'm going to do parentheses, 1 minus the cosine. And I'm going to use x here for a dummy variable instead of t. And then sine of x squared, close parentheses, and then multiplied by the square root of 1 plus 4x squared. Then hit enter. And my calculator, if I did it right, got 2.1705. 2.1705. All right, and so that's what I got. So you ought to try it. Make sure you can do it in your calculator too. Make sure you're in radian mode. Okay. Calculus, we use radians. Pre-cal degrees. All right. Find the area above the xy plane and below the helix, parameterized by r of t equals cosine t, comma 2 sine t, comma t divided by pi. So this is the first time we have seen a parameterized curve in 3 space. So how do we handle this for t between 0 and pi? So what happens is it starts here at 1, 0, 0, and it makes its way up until it stops right here for t equal to pi. So it's increasing in height as my t increases. And if we kept going, it would just keep increasing and make a helix. Just keep going up and up and up. Pretty cool. So I want to find the area above the xy plane and below the helix. That's literally the line integral over the curve C, f of s ds, where s is the arc length parameter. But the trick here is the height is not given by the surface, but the curve itself. Okay, so we don't have an f of xy anymore. We have the z component, which is t divided by pi. Okay, that's the component there that tells us the height, right, at any given t value. So how do we handle this? The curve C in the xy plane is, well, we just drop the z component. C of t is cosine t, comma 2 sine t. So this is the ellipse, right? Let me highlight that part. This is the ellipse on the xy plane here. That's what this represents. And so this is my, how you say, r of t curve. So the derivative of cosine is negative sine. The derivative of 2 sine is 2 cosine. So the magnitude of the derivative of that curve in the xy plane, that's negative sine t squared plus 2 cosine t squared. which is square root sine squared t plus 4 cosine squared t. Yikes. Once again, we're going to have a mess on our hands. Now, what else do I know about this line integral? Well, this curve looks to me like it's closed in the xy plane. Looks like a closed curve. And you remember how we designate a closed curve, C? We put a circle through the integral. So it's a closed curve, C, which has special properties. This is equal to the integral from, well, how did we parameterize it? We never talked about parameterizing it, but, or maybe we did and I just didn't think about it, but it's parameterized from 0 to 2 pi, right? So t runs from 0 to 2 pi. Okay. Times, well, what is the f of x, y here? That's my z component. That's t divided by pi, multiplied by this piece right here. Remember, this ds, all this is, ds, is equal to the magnitude of the derivative multiplied by dt. Okay, that arc length parameter. ds equals the magnitude of the velocity multiplied by dt. So what is that for this problem? This problem is the square root sine squared t plus 4 cosine squared t dt. And once again, I'm going to type this into my calculator. And so if I type it in, math, infinite integral, 0 to 2 pi. I have x, I'm going to use x instead of t, divided by pi times the square root of sine of x. I'm just going to say times sine of x for sine squared. And then plus 4 times cosine x, and then times cosine x, and then I'm going to integrate, and if I did it right, I got 9.6884. Okay. So just to recap, this part right here, integral a to b, f of xy, magnitude r prime of t dt, where this x is x of t and that y is y of t. And for our curve, this was cosine t and this was 2 sine t. Okay? And so we just use c instead of r in this example, because the big difference was this third component represented my height right there. Okay, now one last thing I want to point out for this 4.1 section is that you can have a curve, okay? The key here is that you have a curve that is continuously differentiable, which means it's smooth, okay? Differentiable means smooth. But sometimes you don't have a curve that's smooth everywhere, and so you can do something that's called piecewise smooth. So you remember in Cal 1 we talked about piecewise functions. This is also a pre-Cal topic. A piecewise function be like, maybe it's a parabola over here, and then like, I don't know, a line over there, and we piece them together, things like that. Piecewise smooth curve be like if I had a curve C and the individual pieces C1, C2, and C3 are smooth, but when I put them all together, they're not smooth, or they could be smooth, but it's still a piecewise smooth thing. So to give you an example, I go from A to B, all right, that curve looks smooth. I'm following this path here. So say that's C1, okay? And then maybe from here to here, now I'm going to go sharp dash going this way from B to let's say D. Okay. This curve right here is smooth on that piece right there. Maybe that's C2. And then maybe I have a sharp turn. Try that again. And I stop here at E. Okay, and I travel along that path there. Okay, and this part of the curve is C3. Now look, each one of these individual pieces, C1, C2, and C3 are smooth, but clearly when you look at this path all together, there's a sharp turn right here, a sharp turn right there. That's not smooth all around, but it is piecewise smooth. And so we could break this integral up. Instead of doing the integral C of f of s ds, we could do the integral of C1 of f of s ds plus the integral of C2 f of s ds plus the integral of C3. So break it up over the pieces, and now if I find it for the first piece and then add it to the second piece and then add it to the last piece, then I can get that total area under the curve by that piece right there. All right, guys, that's going to conclude this video.